Imagine a temperature so cold that almost all motion in the universe comes to a stop. No atoms vibrating, no molecules moving, just total stillness. This extreme point is known as absolute zero, or minus 273 degrees Celsius. But what does it really mean to reach the lowest possible temperature? And why is it so important in science? So today, let's dive deep into the mystery of absolute zero. To understand the essence of absolute zero, let's first define what temperature actually is. Temperature is not just a feeling of hot or cold. It is the measure of average kinetic energy of particles. Imagine billions of molecules bouncing around. The faster they move, the hotter it feels. The slower they move, the colder it gets. To put it simply, temperature describes how energetic particles are, how fast they move, vibrate, and collide with one another. Our sense of hot or cold is just a symptom of this microscopic motion. But is there a point where this motion reaches its lowest possible value? To answer that, we need to explore the concept of absolute zero. Now we understand what temperature really is, let's talk about its ultimate limit, absolute zero. Absolute zero is the lowest temperature theoretically possible in the universe. It's the point at which particles have the least possible energy. They can't move any slower. Let's pay attention to the graph of the temperature scales. As you can see, on the Kelvin scale, absolute zero is exactly 0 Kelvin, which equals minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. Unlike the Celsius or Fahrenheit scales, which are based on water's freezing and boiling points, the Kelvin scale starts here, at absolute zero. Approaching this point, classical thermal motion reaches its minimum. However, due to the strange laws of quantum mechanics, which we'll talk about a bit later, particles never become completely still. They retain a tiny vibration called zero-point energy. So even at absolute zero, matter isn't dead. It just exists at its quietest, most minimal form. The idea of the lowest possible temperature did not appear suddenly. It grew gradually, over centuries of observations and experiments. In the 17th century, Robert Boyle observed that gases shrink when cooled. Later, in the late 18th and early 19th centuries, Jacques Charles and Joseph Louis Gay-Lussac showed that gases do not shrink randomly, but follow predictable, measurable laws. These findings suggested that there must be a temperature at which a substance will contract to its smallest possible value, hinting at a fundamental lower limit of cold. Then, in 1824, the French physicist Sadi Carnot, studying heat engines and their efficiency, also concluded that there had to be a minimal temperature at which heat engines can no longer operate. According to Carnot's cycle, setting the cold reservoir temperature to 0 Kelvin causes the efficiency to lose its physical meaning. The mathematics itself breaks down, signaling a fundamental temperature limit. Finally, in 1848, a true breakthrough came from William Thomson, better known as Lord Kelvin. Building on gas expansion data, Kelvin calculated this lower limit at minus 273 degrees Celsius and proposed a new temperature scale that did not start at the freezing point of water, but at this theoretical boundary where thermal motion is minimal. He defined this point as 0 Kelvin, which we now call absolute zero. From that moment on, absolute zero became a clear physical concept, the lowest possible limit of energy. At this point, you might be wondering, if absolute zero is the point where almost all motion stops, then why can't we just go further and stop it completely? Here comes the paradox. The closer a system gets to absolute zero, the more difficult it becomes to cool it further. According to the third law of thermodynamics, also known as Nernst's theorem, it is impossible to remove all thermal energy from any system. To reach exactly 0 Kelvin, it would require an infinite number of cooling steps or an infinitely large refrigerator. As we mentioned earlier, even at extremely low temperatures, atoms still keep a trace amount of motion, the lowest energy allowed by quantum mechanics, known as zero-point energy. Moreover, from the perspective of 19th century classical physics, otherwise known as Newtonian physics, which governs macroscopic objects and celestial bodies, at absolute zero, all atomic energy should completely cease. In other words, the atom should freeze entirely. However, experiments with helium in the early 20th century demonstrated that classical physics is not universal. Heike Kamerlingh-Onnes cooled helium to an extremely low temperature, causing the gas to condense into liquid helium. According to classical expectations, at such an extreme chill, this liquid should have transitioned into a solid, but it did not. This anomaly indicated that, even as temperature approached absolute zero, liquid helium retained too much residual energy to crystallize. The helium experiment provided empirical proof that atoms possess a minimum quantum of kinetic energy, even near absolute zero. The consequence of this discovery was the realization among scientists that a new scientific doctrine was necessary for the microscopic world: quantum physics. Subsequently, Werner Heisenberg formulated the Heisenberg uncertainty principle. This principle states that it is impossible to know both the momentum, which is related to velocity, and the position of a particle at the same time. But why? Well, if a particle were to come to a complete stop, we could pinpoint both values. However, that would eliminate its kinetic energy entirely, which is prohibited by the fundamental laws of quantum physics. It's no secret that every cooling method relies on removing energy from a system, whether by transferring it to another object or by converting it into light and work. But as the temperature approaches absolute zero, there is less and less energy available to remove, and the process becomes exponentially more and more inefficient. And because of this, absolute zero is considered a theoretical limit, a point that we can approach with advanced techniques, but can never actually reach in practice. Now that we've covered the theory, let's turn to practice. How close have scientists actually come to the lowest temperature possible? And what new discoveries has this journey brought into the world of science? Physicists have developed incredibly advanced cooling techniques. It's mind-blowing, but these methods allow us to reach temperatures just billionths of a degree above absolute zero. However, we should make one thing clear from the start. There isn't a single universal way to cool everything down. Different states of matter require different techniques. What works for gases doesn't work for solids. With that said, let's explore one of the most fascinating methods ever developed, a technique that opened the door to entirely unprecedented quantum states of matter. So how does it actually work? Let's dig in. It all starts with laser cooling. Specially tuned lasers send streams of photons toward the atoms. When the atom absorbs one of these photons, It slows down ever so slightly, and slower motion means lower energy, which means lower temperature. Next come the magneto-optical trap. Inside an ultra-high vacuum chamber, scientists created a non-uniform magnetic field combined with intersecting laser beams. This forms a low-energy zone where the coldest and slowest atoms naturally gather and can be held without drifting away or heating up. In simple terms, the trap works like a prison, restricting the motion of atoms and preventing them from gaining extra energy. Finally, evaporative cooling takes over. Radio waves selectively remove the hottest atoms that are energetic enough to escape the trap's potential barrier. After these energetic atoms leave, the remaining cloud becomes colder on average. Repeating this process again and again pushes the temperature down to record-breaking levels. It is important to note that in practice, all these three techniques are almost always used together as sequential stages of a single cooling process. This works like a relay race. One method passes the progress to the next, and the final stage completes the cooling cycle. Just imagine, the coldest place in the universe isn't some distant galaxy. It's a laboratory, here, on Earth. It may sound unbelievable, but this isn't magic. It is the reality of modern science. So, let's take a look at some of the craziest cooling records scientists have ever achieved. 2003, Massachusetts Institute of Technology. Back in those days, a group of MIT researchers cooled a cloud of sodium atoms down to 500 picokelvins. That's half a billionth of a degree above absolute zero. For comparison, the coldest natural temperature in the universe outside of Earth is 1 Kelvin, found at the Boomerang Nebula in the dark space of the constellation Centaurus, located approximately 5,000 light-years from us. The next record was achieved at Aalto University in Finland. Instead of laser cooling, which works best for gases, scientists used a different technique designed for solids: nuclear demagnetization. Using this method, the research team cooled the nuclear spins inside rhodium down to just 100 picokelvins. Thanks to rhodium's unique nuclear properties, the metal turned out to be an ideal candidate for reaching such extreme temperatures. And here comes the current champion, 2018, Bremen Drop Tower. Using the unique microgravity environment of the drop tower, German and French researchers pushed the limits further than anyone before. A capsule containing pre-cooled atoms was dropped inside a 120-meter-tall vacuum chamber. During freefall under near-perfect microgravity conditions, the experiment reached a mind-bending temperature of just 38 picokelvins for about 2 seconds, which remains the lowest temperature ever achieved probably in the entire observable universe. Now, let's think together. So, we've reached the coldest temperature ever, but what's so special about that? And that's exactly the key point. Because the real value isn't in breaking records, but in the discoveries that come with it. Breakthroughs that reveal entirely new states of matter and uncover quantum behavior we've never seen before. Of course, we are talking about the Bose-Einstein condensate, one of the most revolutionary discoveries in low-temperature physics of the 20th century. So, what exactly makes this state of matter so extraordinary? First of all, it's important to clarify that the Bose-Einstein condensate, let's call it BEC for simplicity, is not just an unusual state of a substance, but an entirely new, fifth state of matter. When atoms are cooled to extremely low temperatures, just billionths of a degree above absolute zero, they begin to lose their individual identities. Instead of behaving like separate particles, They merge into a single quantum state, acting as one giant superatom, governed by a shared wave function. In this state, quantum mechanics stops being purely microscopic and becomes visible on a macroscopic scale. Classical physics completely breaks down. Just a century ago, the very existence of a fifth state of matter was only a theoretical prediction by Indian physicist Satyendra Nath Bose and Albert Einstein. Only about 70 years later, the Bose-Einstein condensate was finally realized in practice at Joint Institute for Laboratory Astrophysics by Eric Cornell and Carl Wieman, opening a completely new chapter in low-temperature physics. It must be said that this strange regime, BEC, leads to many other remarkable phenomena and properties. One of the most striking examples is superfluidity. Imagine a liquid with such incredibly low friction and viscosity that it can flow virtually forever without losing kinetic energy. Amazingly, it can pass through ultra-narrow channels that even gas molecules cannot penetrate. Even more astonishing, some superfluids, such as helium, exhibit a phenomenon known as the Raman film effect. In this state, the liquid can climb up the walls of a container and flow against gravity. This happens because friction is almost completely absent, and while the attraction between helium atoms is extremely weak, their interaction with the container's walls is surprisingly strong, allowing the liquid to spread upward. Another property closely related to the Bose-Einstein condensate is superconductivity. Of course, under normal conditions, a Bose-Einstein condensate itself is electrically neutral and does not conduct current. However, the very idea of a BEC lies at the core of superconductivity. In superconducting materials, electrons pair up into Cooper pairs and behave exactly like particles in a Bose-Einstein condensate. Together, these pairs occupy a single quantum state and flow as one coherent wave. Thanks to this, electric current can flow forever with zero resistance, meaning no heating up and no energy loss. All of these discoveries are far more than scientific curiosities. Research into ultra-low temperatures is deeply connected to real human progress and improvements in everyday life. Medicine, transportation, energy, and quantum computing. Ultra-cold physics plays a critical role in some of the most important technologies we rely on. For example, every MRI machine depends on ultra-cold superconducting magnets. High-speed magnetic levitation trains use superconductors to float above the tracks. Superconducting power systems can save trillions of kilowatt-hours by eliminating energy losses. Even global navigation systems rely on extreme cold. GPS works thanks to atomic clocks, which operate using ultra-cold atoms. Quantum computers, built on the same principles, allow us to solve complex problems and equations that are otherwise extremely difficult or impossible to tackle. And finally, particle accelerators, like the Large Hadron Collider, rely on ultra-cold superconducting magnets to accelerate particles to nearly the speed of light. These experiments allow us to probe the fundamental laws of nature, recreating conditions close to the Big Bang and revealing entirely new physical phenomena. So, the true value of these experiments isn't about claiming the coldest spot in the universe. It's about expanding human knowledge and opening doors to technologies that may define the future of civilization. Thanks for watching.